speaker is feedback.
Okay. Yeah. So today I will present some of our recent work in this so-called asympirical analysis. This is a word we made up. So later on I will tell you what this really means. Okay. So let's first take a look at the machine learning paradigm of data analysis. So I use this arrow to indicate this is the sample size. Okay. In machine learning paradigm, so essentially for the empirical methods, we can start with objective function feature selection and then optimize for the objective function, and then eventually we can validate the results. Because the machine learning area comes when data already very large, and then so a lot of emphasis is on the computation. So computation typically is not a big deal in this paradigm. And, but the theoretical analysis is quite interesting. Most of the theoretical analysis rely on this so-called non-asymptotic analysis. For example, the concentration inequality is one of the popular use for this area. And then the nice thing of this non-asymptotic analysis is that a lot of things is very straightforward to get. For example, the sample calculation in statistics typically is a kind of a difficult problem, but in this case, it's really straightforward because in concentration inequality, in particular, precision the result, and then you can straightforward to calculate what sample size you need. Okay, so I call this paradigm as a parallel paradigm in the sense that empirical methods provide evidence for theoretical analysis. Theoretical analysis provide the guidance for the empirical analysis, and then these two methods are coupled together very tightly together in this case. But in contrast, the classical statistical paradigm is quite different because statistics has long history. The classic analysis typically deal with a small or moderate size of data. And we have empirical methods. We still do model building, model selection, model fitting, and eventually we made inference. Okay, and but our asymptotic analysis is quite different. It's theoretical analysis based on this asymptotic analysis. Asymptotic analysis, as name suggests, is for large sample, and then we have typically have consistency of the results and the asymptotic distribution of our estimator, and so on and so forth. So in this sense, this paradigm is not like a parallel paradigm, but rather like a serial paradigm, in the sense that our theoretical analysis is extrapolate the empirical method. Empirical method, we get the results for real data. We kind of interpolate the real data. But the asymptotic analysis or theoretical analysis extrapolate these results to hypothetical large sample. Okay, and then these two analyses is complementary with each other. Okay. And now we are facing another big issue is that now we all have large data or big data, okay? And then our empirical method, because was mostly invented in the old days, and then the computation is really a bottleneck, and then a lot of issues with our empirical method. However, the asymptotic analysis developed in statistical community really fits very well in this paradigm, because our sample size really now is very, very large. Okay, so then the question naturally can ask is that this asymptotic analysis can help to solve some issue of computational issue in empirical methods. Okay, actually, even in the old days, and our asymptotic analysis help us do a lot of empirical methods. For example, most of the statistical inference based on asymptotic analysis. For example, the confidence interval, most of the confidence interval we obtained is through this asymptotic analysis, which simplify a lot of calculation. Okay, so what we want to do here is also the same thing, is is that possible we can use our asymptotic analysis to address a lot of significant issues in empirical computational issues. Okay, so this is the reason we put these words together: asymptotic analysis, empirical analysis, and then we coin this word asympirical analysis. Okay, so the idea is we want our theory to inform the practice. Okay, so this is a very ambitious goal. So now let us take a look at an example so that to see whether we can do that. Okay, so we start with this nonparametric model. Okay, it's a regression setting. It's very simple. So we have a univariate response y, and we have the predictor of features, and then we want to do essentially the regression. But different from linear regression is we have this eta is a non-parametric function we don't know. And then if we assume this random error epsilon is Gaussian distributed, then this is well known, this Gaussian process. Okay.
Excuse me, what do these angle brackets?
Oh, these angle brackets, I try to distinguish. This is the date, this ith observation, but this is the feature, first feature until this feature. Okay. And then in statistics, different from model fitting, we are interested in interpreting the results. Okay, so most desirable results we would like to have is this so-called analysis of variance. And then parallel to the linear regression, we also have this so-called functional analysis of variance paradigm. Okay, essentially this unknown function can be decomposed into the ground mean, main effect, and two-way interaction, three-way interaction, and so on and so forth. And then after integrate this to this paradigm, and then we can interpret our results like in linear regression. Okay. Then the model fitting is typically through these so-called penalized least squares, and then we have this penalty. Okay, and to characterize the smoothness or roughness of these non-parametric function eta, and this lambda is a smoothing parameter, controls the trade-off. Okay, and typically this minimum optimization is performed in a so-called reproducing kernel Hilbert space. In particular, because this is a so-called multiple regression in statistics, we optimize this objective function in this so-called tensor product reproducing kernel Hilbert space. The essential idea is very simple, is for each of these features, okay, in its domain, we construct a reproducing kernel Hilbert space, and then we take a tensor product, putting them together to construct the bigger reproducing kernel Hilbert space. And eventually in this tensor product reproducing kernel Hilbert space, this penalty will equal this weighted summation of certain inner products. Okay, this is essentially a semi-norm in each of these small reproducing kernel Hilbert space. Okay, the troublesome is here is these theta delta here. These are the weights. We also call it as a tuning parameter. Okay, as we have more and more predictors, and then this number grows quickly, actually exponentially. Okay, so give you an example. For example, if we want to have 8 predictors, and then how many these theta delta we need to have? We roughly need to have 92 of them. So these really grows quickly. So made this model not very attractive when you fit this multiple regression problem. Okay. But empirically, how we choose these lambda and theta? Okay, empirically there are many of methods. For example, MALO-CL generalized cross-validation is essentially a numerical stabilized cross-validation in computer science. Okay, we also have some more like Bayesian style, this so-called restricted maximum likelihood method. Okay, all these methods, the computation is very intensive. It's basically in the sample size cubic order, so it's really not very practical if you have a large sample. Okay, so But on the other hand, as I said, in statistics, over the years, we have developed tons of asymptotic analysis in this field. For example, starting from 1982, Bernard Silverman's first paper, we have a series of papers. Okay, if I summarize this literature, okay, essentially we have these simple results. Essentially says, okay, the so-called optimal smoothing parameter is essentially in this order, okay, in this order. This order so depend on two things, R and P. R is related to the order of function, smooth function you want, okay. Typically, in this case, we use smoothing spline to fit the model. And then P is related to the underlying true function, how smooth is that, okay.
So N is the number of your observations, right?
Right, N is the number of observations.
D, the number of features doesn't come in.
Say again?
D, your number of features.
Oh, yeah. D is not in here. Okay, so you can put D here, but it's really not in here per se. Okay, so later on we can say, okay, only this paper explicitly say the D, but all the other papers says you don't need to consider D. Okay, so this should be good enough. Okay, and these. If you remember in the statistics, we typically call something so-called root n consistency. Basically says this is a 1/2. Okay, so but here essentially you couldn't get that order. Okay, you are slower than that. Okay, so because this is a nonparametric regression. Okay, so what this really mean? This is a capital O order of this. So empirically we can interpret this as a constant c times this. Okay, so now the thing is this knowledge, this theoretical knowledge, can really help us to address the computational issue. Okay, so what we did here is really very simple. Okay, our algorithm we present is simple. Okay. So this comes with the simple randomized linear algebra. So essentially, we just take a subsample, okay, of the big sample, okay, and we assume this sample size is B, okay. So still the theoretical analysis is still hold, and then this C we hope, okay, is keep as a constant, okay, and then this is the full sample theoretical results. And what we did is in this small sample, okay, we performed the empirical analysis using, in this particular case, we use generalized cross-validation to calculate the empirical smoothing parameter for us. And then we extrapolate and then to get these, okay? Is this clear? Yes.
So you have a large sample of size n,
Right.
which you think should dictate the smoothing parameter.
Right.
Right. But then to calculate that is too hard, so you're doing that in a subsample.
Right.
But that should have that's a different value n that should.
Yeah. This is a B. This is sample size called B.
And so only the C that you think is consistent.
Right. We now made a strong assumption says C does not change. Okay, so still the same C. And then once we got results, using this small sample, we can calculate this. And then we extrapolate, we get this thing.
Yeah.
Okay, yeah. So this is the whole idea. Okay, so now let's see how this algorithm is simple. Okay, so what you did is in the subsample, you use the empirical method and then calculate these smoothing parameter. You use that theoretical formula, you extrapolate and to the full sample, and then you get it. Okay. So because
how do you recover C then? That constant C, how do you get that then?
Oh, because you already get it here. Okay. You use this divided by this. There is no C anymore.
The next slide, right? The C. No, didn't. There's no C, right?
Right, because as I said, it's remember this.
Right,
you use this divided by this,
Yeah.
and then you know this, you know everything here, and then this will equals this times this lambda delta, right?
You don't need it, okay. I see it cancels out in the ratio, but okay.
Right. Okay. Okay. So anyway, so these essentially, this is the idea, because this is everything is made up according to the optimal theory. So this theory automatically holds. Okay. This is a classical consistent theory for this nonparametric regression. Okay, we was not talking about these details. In practice, how to set up these R and P? P typically you can take 1, and then R you can set equals 3. But then for quite different case, you could choose different thing. Okay, and then what we find is our subsample size typically equals a quarter power of n should be good. Yes, please.
One subsample, or does it help you any to do multiple subsamples?
Yeah, that is a very good question. So what we find, because right now we take a simple random sample that is a uniform sampling, and we find that sometimes it's not very good. So we typically doing several times. What we find is 5 times is enough, and then we take the median of this thing. Okay. And
isn't the implicit assumption that D is much less than N there? Because D is larger than N, you'd need more samples, right?
Right. So here we still assume is like the linear regression we treat is a tau matrix. The N is much larger than the feature dimension. Okay. So, and then we look at the literature. We try to find, is there any other method? Okay. So in the literature, actually, we vaguely find something. Okay. So there is a software manual, and in this manual, they said, okay, because this computation is too tough, okay, they start with some good starting value, and then you just set it there. And then this is the so-called skip method. Okay. In some software, in some R code, okay, there is an option say that you just skip the optimization. Okay, there is other method. There are some theoretical statistician. He just passed away last year, called Peter Hall. In one of his theoretical paper, he just said, okay, let's ignore this constant C. Okay, let's just put it 1 here. Okay, we call it out as order method, and then we compare our method with these two methods using this formula. So this essentially, this is a mean square error of using these 3 methods, and this is the method using this full sample generalized cross-validation, calculate the mean square error, and then we take the ratio and take the log. Okay, and we look at the 3 scenarios. Okay, the first scenario we have 3 predictors, but no interaction. Okay, how many smoothing parameters we have? We only have 3. And then we look at another scenario. We have 3 predictors with two-way interactions, and then we total have 7 smoothing parameters. And in the third case is quite large. We have 8 predictors, and then we look at 28 two-way predictions and two-way interactions, and then we have 92 smoothing parameters, and then this is the third scenario. Okay, so the function we use. Okay, and then we plot these log ratio of MIC. Okay, so each of different color indicating we simulate data using 4 different scenarios of different signal to noise ratio. This signal noise ratio is the lowest, and this is the highest, equals 7. Okay, and then this is our method and the skip method and order method. And in this particular case, this is setting 1, very simple setting, and we can see this order method does not work very well. Okay, the order method essentially just say, okay, this C equals 1. Let's fix the number, and then using this, it seems a lot of variability. Okay, and work not as good as this. The second scenario is there are 3 main effects and 2-way interactions, and then in this case, we can see this skip method begin to work not as good as our method, and then these other methods still have a lot of variability. Okay, And the third method is kind of very interesting in the sense, okay, we still see these other skip method, other method does not work very well, but surprisingly, our method work extremely well, even in the sense it's beat the full sample generalized cross validation because this is a zero line, okay. Yeah. So the reason is also understandable in the sense that because the full sample is taking a lot of time to calculate, and most of the time it didn't converge, and then the program maybe stopped there or converge to some suboptimal. Okay. Okay. And then we try this in couple real data. The first data is these Beijing PM 2.5 data. Essentially, the response is this hourly PM 2.5, and then we have some predictor whether this is taken at what time, and then this dew point, temperature, so on and so forth. Okay, there are 6 predictors. Okay, and the total sample size is roughly 40,000. Okay, and then in this case we fit this model with 9 smoothing parameters. Okay, and eventually we calculate all kinds of these things. We compare this with full sample generalized cross validation because this sample size is not still doable in the supercomputer. So we can calculate the R square. You can see everything we almost very close to this full sample generalized cross validation score. Okay, the results, but our calculation is much faster than using the full sample calculation. Okay, then the next sample is we apply to these molecular dynamics data. In this data, the sample size is really huge. It's almost close to 1 million. Okay, we have 36 main effects here, 7 two-way interactions, and the total number of smoothing parameters is 57. Okay. In this case, there is no way we can calculate the full sample generalized cross-validation result anymore. And so we can only compare this with this skip method because skip method can set up the initial value and then calculate these results. And then in this case, we can see, okay, all our results is much better than this skip method. And also the computation has a substantial say. Okay, so this is pretty much my talk, and thank you for listening.
Questions?
Yes?
Could you sort of just guess this value of C? What if you just tried or lambda, say, you just try lambda as a half, a quarter, an 8, and then see which one does best or something like that? Is that not feasible for some reason?
Right, because typically, according to our experience, okay, these typically this lambda is typically taken in the log scale, and then in log scale there are all kinds of different possibilities, and then we typically have an initial value set up as a certain value, but eventually, even using cross validation, eventually it could converge to any value. So it's very hard to say using grid point to set up an initial range and then using grid point to do the search. Yeah.
Well, that's what is done in practice. At least that's my understanding, right?
Practically, we use essentially some kind of Newton method plus some bisection, whatever, to do this search. But it's very slow. Yes.
So P comes from something that you know about your model, or is it something how is that something you have 100% confidence in?
Oh yeah, that's a good question. Yeah, you need to have some prior knowledge of what kind of, how smooth is your underlying function, right? P taken between the value of 1 and 2. Okay, 1 is sort of smooth, and 2 is extremely not very smooth, right? So you sort of need to put some value there, right? That could be.
How can you do a Newton method if the function isn't very smooth? You just said you're using Newtons, right?
Yeah, but we are talking about the Newton method is for generalized cross-validation. It's not related to the smoothness. It's related to the smoothness of function, but cross-validation is a different function than the eta function itself.
Okay.
Yes.
This is a stupid question since I don't think I'm actually understanding your talk. But so the original O(n) to the power, that's an asymptotic approximation, right?
Right.
So even for the full sample n, so wouldn't the approximation be even worse for the subsample b, or because that's an even smaller, that's even further away from the asymptotic regime, right? Or
So you are talking about our empirical results. Why our method beat the full sample? Is that right?
well, I guess why you would have even thought to try that method in the first place, I guess, because you're talking about applying an asymptotic result to an even smaller sample regime than the original full sample.
Right, that is for our synthetic sample, and then we just want to calculate. The sample size is still manageable, so we still can calculate the full sample generalized cross-validation. Right now, it's essentially the gold, this is the gold standard. We want to compare our method with gold standard.
Okay.
Yeah. Okay.
Okay, let's thank both speakers again.
Thank you.